Howdy, Chapter 15, another form of Newton's law. In the last chapter, it was shown that for a point object, the torque about any origin was equal to the time rate of change of the angular momentum about that origin. It was then showed that this relation also held for a collection of point objects, which means for any real-sized object. In this chapter, we will express the torque and angular momentum in terms of the polar coordinate variables we have come to know and love. This will enable us to solve all kinds of problems that involve rotations and even more complicated motion. We will see that things can get very complicated when the object being considered has an arbitrary shape. Fortunately, things become somewhat simple if the object is symmetric about some axis, and that is very often the case. By considering the angular momentum of a number of small objects welded onto rods which can rotate about some axle, a crude model for any real system, you will see that for symmetric objects, the total angular momentum lies along that axle. In that case, we will have a simple relation between the torque about the axle and the angular acceleration about the axle. External torque equals I alpha, the direction given by the right-hand rule. What enters that relation is the moment of inertia of the object about the axle. I equal the sum of all the pieces times their distance squared to the axle. It is important to keep in mind where any relationship comes from. For example, the total kinetic energy of any system of objects or particles is 1/2 mv squared, summed over all the particles. Only if every object is going in a circle can we write v equals r omega, and only then is it true that kinetic energy is 1/2 I omega squared, where I is the moment of inertia of the system about the axis of rotation. In the same way, it is always true that the external torque gives the time derivative of the total angular momentum. But only if every part of the system is rotating about some axle is it true that the external torque is the moment of inertia times alpha, right-hand rule. Fortunately, this is a situation that does exist in many real and important systems.
This is a nice, simple system, could be a problem on an exam, and it shows the pitfalls of using an equation without knowing where the equation came from. If you had to solve for the time it would take, for example, for the heavier mass to move down through a certain distance, you might say the torque on the system is equal to the moment of inertia times the angular acceleration, right-hand rule. And you might say that the torque is gravity on this side, m1g down, times the radius of the disk pointing that way, m2g times the radius of the disk pointing that way, m2g minus m1g times r is I alpha. You get alpha, relate alpha to the linear acceleration, you've solved the problem. One small problem, you did it wrong. What's wrong? This equation is a result. It's not a fundamental equation. The fundamental equation is that the external torque is R crossed into the external force, which we can write as the sum over all the pieces of their distance from the axle, using F equals ma, mass times acceleration of each piece. We can write A sub I as ARIR plus A theta I theta. The R piece goes away with the cross product. The theta piece gives two parts. One part is the sum of MI RI squared times alpha, right-hand rule. But the second part has this ugly looking term. If we were looking at the disk, every part of the disk is going in a circle, so dr dt is equal to 0. For the disk, torque equals I alpha. But if our system also contains these two masses, these masses are not going in circles. They do not have 0 for dr dt. do not pass go, do not collect $200. If we want to solve this problem, understanding where the equation torque equals I alpha came from, we realize we have to isolate just this system, in which case the torque external is the tension in the string times the radius on this side, the tension on this side times the radius on that side, of course the same. And so we can use torque equals I alpha, but only for those parts which are going in circles. So we would have to isolate this body and use F equals ma, isolate this body and F equals ma, and then use this system, torque equals I alpha.
Summary. The fundamental but confusing quantities defined in the previous chapters are expressed in terms of polar coordinates. This leads to useful but often complicated relations between the variables. For the special case of symmetric objects, the relations become simple in terms of the moment of inertia about an axle. There we have, for example, the useful result, external torque equals I alpha, which can be used to solve many problems. One does have to be careful, as is always the case, to be sure that this result is only used when the condition for its validity is satisfied. Gig 'em.